Hi everyone, this is Mr. Lee. In this video, we're going to go over apparent weights. Alright, so let's start off with the definition. Apparent weight is how heavy you feel. It's important to make a distinction that how heavy you feel is different from actual weight. Alright, so let's go into a couple of ideas. So apparent weight is how heavy you feel, and it's different from your actual weight. Before giving you the actual, the formula for it, let's go over the idea behind it. So let's say we have you. You are standing on a surface. Hello. Okay. We know that your actual weight is f of g. So f of g going down is equal to mg. So this is your real weight. Now, weight is just how heavy the planet or different planets are pulling you towards the center of the planet. So if you're on a surface here, there's one more other force that's acting on you, and that's the surface force, F of n. So in this case here, because we are in equilibrium, your F of n is equal to your F of g. And so the idea is, in this case, your real weight and your normal force are the same. And so if we just replace a word of normal force to apparent weight, then you have the idea of what apparent weight actually means. So F of n, or the normal force, is your apparent weight. All right. Now, this is important because, when we're just standing there, right, if you're just standing there on a surface, you feel your actual weight. Okay, but the idea of apparent weight is actually coming from how hard the surface is pushing up on you, not how heavy the earth is pulling you. Okay, so that's the distinction there. It has to come from the surface. So for example, let's say we have you, okay, and then we give, I don't know, let's put a book bag on you. All right, so this is the book bag. All right, so we have a book bag that's on you. And so in this case, right, if we were to look at this as a system, okay, your mass overall, so this is you and book bag, because you're wearing the book bag. I'll put that book bag right there. Okay, so this is your book bag. All right, so here, your weight overall has increased because we're looking at this system as a whole. So your Fg has gone up. Now, the idea here is your real weight hasn't gone up, right? It's just that because you're wearing a book bag, the overall system, the weight of the system goes up. But here's the important part. When you wear a book bag, especially if it's like a super heavy book bag, your F of n also increases. And that's because how hard the earth is pulling on you against the surface has to push back with the equal amount of force. So let's say your real weight is, 700 newtons. Okay, and your book bag has a weight of 100 newtons. So your real weight is 700 newtons, okay, but you feel a total of 800 newtons. So you feel heavier, but you actually didn't get heavier, okay? That's a big distinction. So F of n is how you feel. Let's do another example. So let's say, you go on a trampoline. All right, so you're on a trampoline and you are above the ground here. So when you are in the air, whee, okay, whoa, right? So you're doing yay, I'm having a good time. Okay, so you're screaming for joy. So here, if we were to draw the free body diagram, we have just F of g. Notice your F of n is 0. Now, this is really cool because in this scenario here, if F of n is how you feel and your F of n is 0, in this case, we say we feel weightless. Ooh. Now, that sensation that you get when you're mid-air is the same sensation that you'll have if you're like an astronaut and you're up in space and you're floating. Because in space, if you're floating in space, right, if you're floating in the middle of a space station, you're not touching a surface. And if you're not touching a surface, you feel weightless. And you're weightless because you're also in space. You see how it all kind of just ties together? Cool stuff. All right, now what about elevators? Okay, so elevators. Let's say you're riding an elevator. Yay, you're having a good time, right? You're riding an elevator. Okay, so you ride the elevator, you push the button, and you're about to go up. So when you're about to go up, so let's just draw a free body diagram, right? So this is your normal F of g. All right, so this is F of n. Okay, so right now your velocity is 0 and your acceleration is 0, right? So the elevator's not moving. There's no reason for the elevator to move. So here you feel your normal weight. But as soon as you push that button and the doors close, right, and the floor rises. Okay, so what the floor is doing is pushing up against you. But more importantly, if we take a look at the system as a whole, what's happening is you have a acceleration that is up. Now, before we looked at this scenario and we said that we are in equilibrium. But if we have a net acceleration that's up, the free body diagram, instead of looking like this, will look a little bit more like this. All right, so here we have our f of g. I'm going to exaggerate this. There we go. Okay, so you see how this normal force got a lot bigger? And that's because we are accelerating upwards. The floor is pushing up against you. So in this case, when you first rise up in an elevator, you actually feel heavier. All right, so the elevator is rising and is rising and is rising, but during that rising part, a lot of the times the elevator is moving with constant velocity. So that middle part of your journey, you feel normal, right? So you feel like your normal weight. All right, so you're about to reach your destination, okay? You're about to reach your destination. Now, when you're about to reach your destination, our velocity is up, but we're slowing down. Ooh, okay, so this goes back to kinematics. So if we're about to slow down, that means our acceleration has to be in the opposite direction of your velocity. Your acceleration is down. So if I were to draw my free body diagram, right, so this is your f of g, but we know our acceleration is down, that means that this f of g has to be bigger than your normal force. Okay, because if you add this positive f of n plus this negative f of g, if your negative f of g is bigger, that means your acceleration is also in that same direction. So in this case, when you're about to arrive at your destination, you have this funny feeling in your tummy, okay, and you feel like you weigh less. Okay, now if there comes a point where, if, like, let's say the floor suddenly stops, okay, if the floor suddenly stops, that means that you actually get launched up, and then this f of n approaches 0, and so you would start to feel weightless. So you go from your normal weight to feeling weightless. So if I were to do a quick little graph here, right, of our journey, and let's just say this is your f of n. Okay. Let me draw this line underneath here. Sorry. Okay. So this is time. All right. At the very, very beginning, okay, when you're in the elevator and the elevator doors close, oops, that's not right. You would feel your normal weight. All right. So I'm going to say here in this part here, elevator, the velocity is 0 and your acceleration is 0, so your f of n is equal to your f of g. All right, you close the elevator door, and let's say we're rising upwards. So when you're rising upwards, all of a sudden, your normal force, it starts to increase. Okay, it increases. And then here, we can say this is when our velocity is up, our acceleration is also up, and we are speeding up. All right, and so here our f of n is greater than f of g, and so here we feel heavier. All right, and then that f of n, it approaches back to normal, right? And so here we're just rising here, and here we can say our f of n is equal to f of g. Our velocity is still up, but our acceleration is 0. We're not speeding up, or we're slowing down. Okay, and then when we're arriving at our destination, our acceleration becomes negative. Okay, so we actually start to feel a little bit. Whoops, I went a little too far. Oop. Okay, we feel lighter. Ooh, right? And so here we can say our velocity is still up, but our acceleration is down because we're slowing down. And so our f of n is less than f of g, and we feel lighter here. And then we reach our destination. So when we reach our destination, we return back to our normal weight. Cool stuff. All right. Yeah. Let's do the elevator down now. Okay. So when we are in an elevator and we are going down, okay, so here we get in the elevator, we're about to go down. Okay, so initially our f of g and our f of n, they are identical. All right, we push the button and we're going to go down to the bottom floor. All right, so in that case, our acceleration is going down. And so what that means is that your f of n has to be smaller than your f of g. Okay, that way our net acceleration is pointing down. So I'm going to draw f of g a bit bigger than your f of n. Let's make your f of n a little bit tiny. There we go. Okay, and so when you first go from the top floor and you're approaching the bottom floor, right, as you first get in the elevator, you feel lighter. Okay, and then the middle part, right, the middle part here, your f of n and your f of g are identical. Okay, so you feel normal, and we're about to arrive to our destination. Let's say we're arriving at the bottom floor. So here our velocity is down, okay, but we have to slow down, right? Because we're about to reach our destination, and we don't want to speed up when we reach our destination. So we are, I'm gonna write this over here, we're slowing down. So if our velocity is down and we're slowing down, that means your acceleration is upwards. So what happens is that the floor is pushing up against you, okay? And so here we can say, whoops, let's get rid of this here. Our f of n, yeah, it's pushing up against you, so that's like it's trying to slow you down. And so we actually feel heavier. So we feel heavier as we arrive at our destination. All right, now mathematically, this is also true. So let's take a look at the formula. So when we are in equilibrium, we say that f of n is equal to f of g. Right, but if we were to take a look at the line before that, we will say f equals ma, right? And we say that our a is 0, so m is 0, and our net force is equal to f of n positive minus f of g. All right, so starting from this line here, we can algebraically go from that line to this line. All right, so this is when you're just standing on the elevator, nothing is happening, okay? Or you're in the middle part when you're moving with constant velocity. We are in equilibrium. All right, now let's do the math for when we're about to rise. All right, so when we're rising, okay, starting off with Newton's law, we say that f of n minus f of g is equal to ma. So I'm going to do a quick little sketch. So when we're rising, we know our f of n is bigger, and we know our f of g is smaller in comparison, but acceleration is positive. So if we're looking for how heavy we feel, remember we kept on saying that we feel heavier, if I move my f of g to the other side, whoa, would you look at this? We get f of g plus ma. So I just want to point out right here, okay, f of n is equal to f of g. This is how you feel normally. Right? What I just highlighted is what you feel normally, but look what we just did. We just added to how you feel normally with m of a, and that a is whatever the acceleration of the elevator is, and m is your mass. Okay? And so you feel heavier mathematically as well. All right? What about when you're slowing down, right? You're about to arrive at your destination. So when you're arriving at your destination, our acceleration is downwards. Okay, so we have f of g, and here we have a tiny little f of n. All right, so let's start off with Newton's law. F equals ma. It's still like this, but watch what I do here. You see that a? I can't put it as a regular a because a is pointing down, and down is negative. So this is actually negative a. Whoa. All right, so when that happens, mathematically, if I rearrange it, if I put f of g to the other side, we get positive f of g minus ma, and because that minus comes from that negative a there. And once again, I'm going to point this out. F of n is equal to f of g. That is how we normally feel right here. This is how we normally feel. But when we are arriving at our destination, or when our acceleration is in the opposite direction of our normal force, look what happens mathematically. We are subtracting from how we normally feel, so we feel lighter. All right, well, that's it. That's apparent weight. I'll see you next time. Bye-bye.